If you recall the introduction to the IO algorithm, we saw this problem of traversing a linked list. And we saw that if we do not pay attention to how the blocks are created or how do we do block access, we could actually do lots of IOs to do this traversal of the same linked list. So here we're going to actually solve this problem. So the problem we're going to look at is that we have a linked list of size n, and what we like to do is to assign a rank to each element of the linked list. So for example, the first element of the linked list will have rank 1, the next element of the links will have rank 2, and so on. So basically something like this. Okay. Obviously this linked list is not stored in a sorted order, because if it was, then it would be an easy problem. So another way of saying this is that we will actually like to sort the linked list, but of course the problem is that if I just look at an element of the linked list, we have no idea what is its rank, because its position on the disk might not tell us anything. This problem is actually one of the simplest graph problems that you can think of, and in fact the techniques that are used for this problem can be generalized to solve more complicated other graph problems as well. Of course, in the internal memory it's easy to traverse a linked list in linear time, and of course you can also do the same thing in the IO model, but if you do that then you get n IOs, which is pretty bad. Obviously this is kind of a sorting problem, so therefore we cannot do better than sorting bound, but actually getting the sorting bound is quite a bit challenging. Okay. And in fact the solution that we're going to look at solves a more general problem. In this more general problem, you will also have a weight assigned to every element, or every edge actually. In the list ranking problem, all the edges are assigned weight 1. But in general, you could have edges with arbitrary weights. And what you want to do is for every element of a linked list, you want to sum up the weights in all the edges that come before it. So for example, this first element will receive value 1 or rank 1 because it is connected with an edge of weight 1. This is value 2 because I have 2 edges of weight 1 connected to it, and so on. The reason we do this generalization is because later on we're going to use a recursive algorithm that requires us that we deal with an input that has weights other than 1. Right? So therefore we do this generalization, and it turns out that the solution that we're going to look at actually solves this more general problem. Okay, I will quickly go over the basics of the algorithm, and then in the future videos I will fill in the detail. So the algorithm basically looks like this. It has 4 different steps. In the first step we find an independent set of vertices of the linked list. By independent set, what I mean is that there is no edge between these blue vertices, blue linked list elements. Okay, so they are completely independent. After finding some independent set, and actually here we would like to find a large independent set. Okay, so after finding a large independent set, let's say marked as blue here, we remove them. Okay, what does this step do? Basically, remember that this is the previous element of this blue, this is the next element of this blue. If I remove this element and if I add an edge of weight 2 going from this element of linked list to that one, I do not change the rank of any other vertex in the linked list. Okay, so that's basically what it means to bridge out. To remove this element and then add up the 2 links that we deleted and put it as the weight of this new element, a new edge of 2. Of course, this means that if I delete this element, I will delete these 2 edges and instead put an edge with weight 3. Okay, because we add 1 and 2 and then to get to 3, and so on. So that's what bridging out operation do. And once we bridge out a big fraction or a constant fraction of the elements of the linked list, we can recurse. We recursively compute the ranks of the remaining elements, and then the only thing left to do is to bridge in to compute a rank of the elements we just deleted. But since they were independent, plugging them back in is actually quite or relatively easy, it seems like, because I just need to plug in the edge that I've forgotten. I know the rank of this one, so therefore I could easily compute the rank of this one. Okay, we're gonna look in more detail how we do this, but this is not the difficult part of the algorithm. Okay, and that's basically how the solution goes on. And if we can do step 1, 2, and 3 in sort IOs, then we're done. Step 3 is obviously a recursion step, so there's nothing we can do about that. And then the recursion ends up being something like this. If you can find an independent set of constant or a big enough of size, say alpha times n, in other words a constant fraction of all the elements, then in the recursion we have at most this much to recurse, and then this is the cumulative IOs that we spend for steps 1, 2, and 4. And if you look at this, you'll see that this forms a geometric series, right? Because if you just look at this recursion, there is only one term in the recursion, so therefore we're just recursing on a smaller and a smaller fraction of the input. And then it turns out that this recursion solves this to this much IO, specifically because T of M is O of M over P, right? Because if the linked list fits inside an internal memory, I could just read the entire thing using M over P IOs into the internal memory and just solve it using normal internal memory solutions. Okay, so with this base case, if this is the base case, then this recursion will solve to exactly the sort IO. So then we'll be done. So in the remaining videos, the only thing we need to cover is how to do the steps 1, 2, and 4 in sort time.